Hello again, and welcome to another video lesson with Takoa Lawson. We're starting our next topic, which is one-dimensional motion in AP Physics, also known as 1D kinematics. Isaac Newton, who came up with the laws of motion, a lot of the work that Newton did was actually based on other scientists' evidence. It was actually based on data collected by other scientists. Galileo, who first really started examining motion, and a lot of people had beliefs or opinions about what motion was of different objects, but nobody had really tested it. Galileo was seeking to understand motion, and rather than just believing or making up what he thought was true, he decided to empirically test and come up with different ways of measuring motion. And by careful measurement and careful analysis, he was able to describe motion much more accurately and much more correctly from misconceptions that people had that he corrected. There's all sorts of philosophers and all these different people that had these ideas that without data to support it, they just made claims that people said, oh, they're very smart, so they must be correct. He was very smart, but instead of just letting his intelligence make the claim for him, he let the data make the claim.
Galileo had spent half a lifetime trying to prove the Earth moves. Now, he would come to terms with something much more basic, the mathematics of motion itself. But motion is hard to measure.
It all happens just a bit too fast for you to see what is going on. Galileo hit on this wonderful idea of slowing down the motion. So instead of trying to watch a thing falling, he rolled balls down very gentle slopes so that the speed built up very, very slowly.
Galileo reasoned that as balls rolled down slopes, they would accelerate, just as they did in free fall, but more slowly. As a young man, Galileo had designed a very accurate inclined plane, one of the most important pieces of experimental apparatus in the history of science. Galileo left behind no plans for his inclined plane, but based on his experimental notes, Professor Roberto Caparelli is using what he believes to be Galileo's original design to discover how he was able to accurately measure acceleration.
Galileo studied the inclined plane, slowing the motion of falling bodies until he was able to observe the phenomena. He was able to measure exactly how fast a ball would roll, timed with the swing of a pendulum. Galileo was sure that the steady acceleration must be governed by a mathematical rule.
So he takes this very gentle inclined plane and he lets the ball roll down, and he watches how that ball speeds up, and he measures how far it goes in a certain time. And then he makes his first empirical discovery that if in the first unit of time it goes 1 unit of distance, in the next unit of time it travels 3 units of distance, and in the next 5, and in the next 7. So it has this beautiful numerical progression, 1, 3, 5, 7. And he calls this the odd numbers rule. And he really is entranced by this. He knows he's made a huge discovery.
Galileo had found a mathematical rule for accurately predicting the motion of objects in the real world, a universal law which applied to any falling bodies.
Underneath this beautiful empirical law that he found a deeper law, clearly a deeper law, using mathematical logic and deductions. And this was actually the key to all the later great successes, first of Newton and then of Einstein and all the other wonders of modern science.
As a young man, Galileo had revolutionized astronomy. But at the age of 74, his last great book revolutionized the physics of motion.
From the point of view of physics, his most important contribution is his discourse on the 2 new sciences. Indeed, it's that book that provides the real foundation for Isaac Newton.
So we want to know what motion is. We want to be able to describe motion without thinking about why it happens. But before we do that, we have to be able to tell the difference between an object and a system of objects. And then we also want to know the difference between a system that's open and a system that's closed. The most basic and easiest idea is an object. An object is simply some chunk of material, something in the universe that we start paying attention to. Most of the time it's made up of atoms, so it'll have mass. We might be looking at the motion of cars, we might be looking at the motion of a person. We could even be looking at the motion of a single molecule in the air, but since that molecule is made up of atoms, it has mass. An object, or a body, is pretty straightforward. It's something with measurable properties, some object we're starting to look at. It's an isolated body when there's no other bodies that it can interact with, or if there's any other bodies that it's interacting, we're not paying attention to them. They're not being included in our system. They're not being included in what we're looking at. So an isolated body is simply a chunk of material or an object that we're looking at. We ignore any internal structure. So if it's a ball that has inner parts, but we're just describing the ball, we don't pay attention to the inner parts. And it will have specific properties, things like mass or volume or temperature. Velocity would describe how much it's moving. In the universe we live in, you have objects that aren't isolated. You have objects near other objects that are able to interact. That steps away from being a single isolated body or an object to being a system of objects. A system, there's multiple bodies that can interact, or we might have an object or a body that has inner parts that we're not ignoring, that we're looking at those inner parts, and then that becomes a system because those inner parts become the individual bodies that are interacting with each other. That system allows different objects to run into or bounce off of each other, allows different objects to transfer energy from one to another. In a system of objects, you have many more interesting phenomena going on. But if we're really going to start looking at motion and we just want to understand motion, the best place to do that is starting with an isolated object. Let's just look at a single object and be able to describe its motion accurately. And then once we can describe the motion of a single object, maybe then we can start working on how objects interact with each other. Another idea that's going to become important when we talk about systems of objects. That system could be a closed system, which is an isolated or insulated system, meaning that nothing can enter or leave the system, neither things made of mass or things made of energy. If it's a perfectly isolated system, there's no way of getting into or out of it. While if it's an open system, energy or mass can travel through the boundary between the system and the universe. When we're looking at a system that's isolated, since nothing can enter or leave it, all the laws of conservation are true. If it's an open system where we can have either forces coming from outside the system, we can have energy entering or leaving the system, in the universe, the laws of conservation would still be true. But where we're paying attention to in our system of objects, we could actually see a net increase or a net decrease in one of these areas. Not because the law of conservation is being violated, but because some of what it is that we would need to account for to get everything has either entered or left what we're paying attention to, or our system. In addition to being able to describe the difference between system of objects and a single object or an isolated object, which are one of the big ideas or the key ideas that will definitely be tested on the exam, we want to be able to understand frames of reference. Who's paying attention from where? What are they doing relative to whatever they're observing? Those reference frames are exactly what they sound like. In order to have a reference frame, we have to have a coordinate system. You can't describe anything inside of space without some kind of coordinate system to be able to do that. And we'll talk about some of the coordinate systems we're going to use throughout the year. In order to have a coordinate system, you have to first not only agree on some rules for describing different directions within that coordinate system. The directions are meaningless without some origin point or without some point of reference for where those directions are based. One of the important keys of a reference frame is that there's a point of origin. It's arbitrary where we choose to put that point of origin. Thinking about the solution or thinking about the problem and the way I'm trying to describe it, and picking an origin point that makes it easier for me in my description, that makes it easier for us when we're trying to go through the data and trying to analyze what we know. While it doesn't make sense to purposely want to use many reference frames, we could be asked for observations between two different reference frames and being asked about how they compare, how are they similar, how are they different. You can have multiple reference frames, they all can be related to each other. An inertial reference frame is simply a reference frame that has a constant velocity. So a reference frame with zero acceleration, that's an inertial reference frame. A reference frame that has a acceleration that's not zero is a non-inertial reference frame. Almost all the time we're working within inertial reference frames. because the inertial reference frame is really when all of these descriptions that we're going to use in kinematics are most easy to apply and always true. It's impossible to tell if the inertial reference frame is moving if you're inside of it moving with it. Sometimes you get some clues by being able to see other frames around you. For instance, if I'm in a car and I'm moving at a constant velocity, I can tell I'm moving because I look out the window and I see the objects going by. However, if the windows were tinted or if they were painted or there wasn't any way of being able to see that reference, I wouldn't know whether I'm moving or not. My experience inside a car, all the laws of physics inside a car moving at a constant velocity would be the exact same as a car not moving. The car is a little bit of a strange example because it's very common you hit a little bump so you get a little acceleration. You take a turn so you get a little acceleration. It's very difficult to be in a car and have a constant velocity exactly. There's a couple of places that it gets them a little bit more easy to see, like an airplane. In an airplane, you're moving extremely fast, but you don't feel like it. When you're sitting there, you don't get thrown to the back. You do when you're taking off, and then you get thrown forward a little bit when you're going landing because there's an acceleration. If you're turning or you hit turbulence, then there's accelerations. But if you're in the airplane at the cruising speed, when you walk from the back towards the front or from the front towards the back, you feel like you're just walking at the normal rate, even though you're moving at hundreds of miles per hour. Even more extreme is thinking about being on Earth. Earth is moving at many, many, many more times faster than an airplane. But when we look around, we feel like we're not moving at all. And that's because relative to the Earth, we're not moving. So the Earth would be an example of an inertial reference frame. It's moving at a constant velocity. We'll work more on what it means to be an inertial reference frame or a non-inertial reference frame later in the year. In addition to being able to tell the difference between an object or a system of objects and an open or closed system, or an inertial reference frame versus a non-inertial reference frame, we also have to be able to use this idea that a reference frame is defined by a coordinate system. And we have to have some origin and then define our coordinate system around it. We're going to look at very quickly at some coordinate systems, most of which you'd be familiar with. The ones that we're going to be using a lot, you're very familiar with. A couple we're just going to mention because they could come up later on, not so much in this course, but if you decide to go into a more advanced science as you go into college, or depending if you do any kind of engineering or architecture, it may come up. We'll start with some pretty simple and straightforward, or the coordinate systems that you've used often to be able to describe things around you. The first coordinate system, or the most simple coordinate system, is a one-dimensional coordinate system. This is a coordinate system that you're able to move forward and backward along a straight line. Okay, so I can move forward or backward. That doesn't really help me identify a direction. So we could start assigning things that we're used to for direction, like moving east or west. But then how do I know where east is? I have to have some kind of place that I designate that from that point moving in this direction is east, and then if I turn around and move in the opposite direction, that's west, or vice versa. If I move west and I turn around and move in the opposite direction along that line, then I'm traveling east. Another way that we do that is if we imagine our origin being at this 0. While we could call one direction east and another direction west, we could also call one direction the positive direction and one direction the negative direction. So we could say, well, we moved 2 meters in the positive direction, or oh, we moved 2 meters in the negative direction. So positive and negative just allow us to have two different directions along the number line. Have to be a little bit careful about the positive negative numbers. Mathematically, -2 is a smaller number than +2. If I move 2 meters in the negative direction, that's -2 meters. If I move 2 meters in the positive direction, that's +2 meters. Physically, I have moved the same distance in either direction. Physically, I have the same displacement in either direction. But mathematically, -2 is a smaller number than +2. So just be careful about that idea. When you have -2 and +2, that's not as confusing. Where students get caught up on this sometimes is when they're comparing something like a number like -4 and +2. In the world of physics, if we're using negative not as a description of a negative number, but as a description of a direction that's an arbitrary decision because we've just made one direction positive and the opposite direction negative, moving 4 meters in the negative direction, you have moved a greater distance than moving 2 meters in the positive direction. If you move 4 meters in the negative direction, your displacement is 4 meters. However, mathematically, the number -4 is smaller than the number +2. So this is an important thing to be an intelligent person about and recognize the difference between describing the universe we live in, making a coordinate system, and understanding how math principles work when you're describing positive and negative values and whether something is larger or less than another. We can look at this and move anywhere we want. A lot of times we imagine starting at the origin, and that's convenient. Wherever we start observing our body or object, we'll make that 0. We don't have to. We could very easily observe the object starting when it's at the positive 6 meter point. Or we could easily start it at the negative 8 meter point. Where it moves is going to be very important, whether it moves in the positive or negative direction. When you're moving in the positive or negative direction, it allows us easily to identify one direction and the opposite direction. The difference is, on a number line like this, positive has to be to the right and negative has to be to the left in the math world. You don't have a choice. However, in the physics world, since all we're doing is assigning a coordinate system and it's an arbitrary decision, we could make the left positive and right negative if it's convenient for the data we're collecting or for the analysis. Usually, and I tell you to do whatever you're comfortable with, students tend to do what they're used to on number lines, what they're used to in their math classes. Right is positive, left is negative, and you can always stick to that and be consistent, and it makes it easier. But when you get comfortable with the idea that it's just a coordinate system, instead of working with negative numbers because something's moving to the left, you can just make the left the positive direction, and then you only work with positive numbers, which isn't necessarily going to make things a lot easier, but sometimes you run into a few less errors. In a two-dimensional coordinate system, not only can we move forward and backwards along one number line, there's a number line that's 90 degrees to that. If you look at this, and you imagine that first number line being here, where the positive x to the negative x, then we take another number line here, the negative y to the positive y, and we lay it right across the top of it at 90 degrees. Where they intersect becomes the origin. And now we have the ability to move in the positive or negative direction along two different lines. It's no longer a line. What that creates is what we refer to as a plane or a surface, right? That ends up creating a two-dimensional surface. So now we can move anywhere, not along a line, but anywhere inside of a plane or anywhere along that surface. It's really important in the two-dimensional plane, which is much more common. We'll still use positive and negative values, but we start to get into some more interesting options. Just like with the number line, I could have used east or west. Technically, I could have used north or south as long as they were opposite directions. When we start dealing with the two-dimensional system, it starts to become more convenient to not just have positive x, positive y, negative y, but to be able to describe these in terms of east and west, or perpendicular to that, north and south. That makes sense if I'm on the ground and I'm moving around the surface of the ground. But what if I climb a ladder? What if I go up some stairs? That's not the same as going north or south or east or west. Oh, but I can take that plane and I can rotate it. And now I could have that y-axis be going up and down instead of going north and south. So it's not north or up. That points in the north direction, it's north. If that points in the vertical direction, then it's up. In a surface or a plane, since it's a flat piece of paper, it can only point in one set of two directions. You can have east, west, up, down, or you can have north, south, east, west. But you can't have east, west, north, south, and up and down in the same plane or in the same two-dimensional surface. What really gets interesting was you add the third number line, and again, just like the other two, you make it so it's perpendicular, it's at 90 degrees. Here we see our x, which goes east to west. We've orientated our y perpendicular to it, but making it so that it goes above and below, and so that would be up and down. And then our z, which is perpendicular to both of those, which creates a third dimension. It creates another plane that could now go north and south. Or where you have a three-dimensional axis, where there's three different axes all at 90 degrees to each other. Now you can move north, south, east, west, or up and down within this coordinate system. This one allows you to move in all three directions. What you notice here is there are three different planes, or they describe three different ways in which they can move relative to each other, and it's no longer a plane. A plane is only the two-dimensional system. Now they describe a volume or a box that you can move around within. The interesting part about this is that One-dimensional system is much easier. You only have one value that you're describing moving in a positive or negative direction if you're changing position. In a two-dimensional surface, it starts to get a little more complicated. You have an x and a y value. You have to describe how you move in the horizontal or the x direction and how you move in the perpendicular direction or the y direction. In this three-dimensional system, you have three variables. You have to describe the x, the y, and we call that third dimension, or that third axis, z. Again, we still use positive and negative values, not to represent actual positive and negative numbers. They turn out mathematically, we will use negative numbers to be those values, but really to identify moving in one direction and then moving in the opposite direction. And it's just saying going one direction and then the opposite direction, which technically does work. It's easier and more convenient to call one direction positive and then understand or apply that the opposite direction is negative. You also see here, instead of calling them x, y, and z, we could refer to them as north, south, east, west, up, and down. It's actually arbitrary that we've made x, east, west. In general, a lot of times you find that that's true, but I could have just as easily made the x-axis up and down, or the x-axis north and south, and the other two axes would still be 90 degrees. It's just that once the x-axis is used for north and south, the other two can't be north and south. They have to be perpendicular to it. One of the ways to visualize or to try and get your mind around what the three-dimensional system is to use your hand and orientate it so that all of your thumb, your pointer finger, and your index finger are all at 90 degrees to each other. Now, if you orientate it like that, what you'll notice is right here, this one, the thumb points out, pointer finger points up, that's approximately a 90 degree. So what we'd see there is if we call this x, the horizontal, call this y, the vertical, then z actually goes into and out of that plane and would go towards the camera or away from the camera. Again, it's arbitrary, so I could actually rotate it like this, but we'd still see the same thing. Now this represents that horizontal or x, my thumb represents the vertical or y, and my pointer finger represents the z that goes into or out of the plane, although I could have made that x, this z, and that y, but what you see is how they all orientate relative to each other. A volume, an area in which if I was moving anywhere along all three of them, I could move anywhere within that space relative to the origin, which is where all of them intersect. The last coordinate system is referred to as the polar coordinate system. A polar coordinate system is a little more convenient in some situations, although it's not as common in your everyday experience. Most of the time you work in that Cartesian system where we describe things either as x's and y's, or x's, y's, and z's in terms of different points inside of a volume, different points on a surface, or different points along a line. Polar coordinates allow you to identify all of those same positions. There's actually nowhere where you could use a Cartesian system that you can't use a polar system, and nowhere you could use a polar system that you can't use a Cartesian system. In many ways, a polar system is actually easier to use because there's less variables. However, because it's not as common and because you don't learn about it as much as a younger age, it makes it so that most students prefer to stay in the Cartesian system. We have to be able to work within both, and you're going to see a couple of instances where you'll really prefer to use one over the other. What you really want to be able to do for your different reference frames, for your different coordinate systems, is be able to move between either of them at leisure, and that's one of the things that we're going to work on. When describing a polar coordinate system, the easy way to visualize is shown here, angles that start at the positive x-axis. So if you imagine 0 to 180 and 90 to 270, creating your x and y like you're used to on a Cartesian system, that 0 is now your positive x-axis relative to the origin, the black dot in the center. The polar angle increases in a counterclockwise direction around that origin. So that's one of the keys. In a two-dimensional polar coordinate, one of the variables is the angle. That angle, whether it's 0 or 30 or 60 or 90, would be along any of those, although it could be something like 23.2, that would just be somewhere in between 0 and 30, and you'd either have to have a protractor, so a way of getting that angle, or not draw it to scale. The other part of a polar coordinate system is what we refer to as the length of the magnitude. It tells you how far away from the origin you would have to move. And so if you think about these concentric circles, Imagine this being 1, and then the next one being 2, and then the next one being 3. What ends up happening is if we had an r, or a length of 1, we would go to that first point. If we had an angle of 0, then we'd go from the origin to that point on the 0 degree. If we had an angle of 60, then we go from the origin to that point on 60 degree. And so what we end up describing is lines at different angles. That's what polar coordinates do. They give you a length of the line, we're going to refer to that as r, and they give you an angle of the line, we're going to refer to that as theta. Length from the pole or the center, angle based on the positive x-axis being 0 degrees and moving in a counterclockwise direction. A negative angle would be moving in the clockwise direction. Here we see a different way of representing it where it's showing a little more clearly the black line here where we have 0, 1, 2, 3, 4, 5, 6. So different r's would be different lengths from that pole or that center to those points. So for instance, a r of 4 would go from 0 to 4. And an r of 4 with an angle of 75 degrees wouldn't travel along this segment. It would go from here up this segment. So that would be where we'd find something like 4, 75. So there's two parts to a polar coordinate. There's two parts to an xy coordinate too, but it's different. Xy coordinates tell you where along the x and where along the y to reach that point. Polar coordinates give you that same data, but instead of giving you the x and y values, they give you the length or the distance from the center or origin and the angle at which you have to travel to get to that point. Technically, we can have a three-dimensional polar coordinate system as well. We could be traveling along that surface, but we could also add another variable, phi. So we have r, which would be the distance or the length from the pole or the origin. We have theta, which would be traveling around a plane in a counterclockwise direction. And then we can have phi, which would be traveling perpendicular to that or coming out. It's kind of like the z-axis went towards the camera away from it. Imagine my hand being the surface or the plane and we're doing the polar coordinate system. This would be your positive x-axis, and you would rotate around it in a counterclockwise direction. Anywhere on my palm would be our normal two-dimensional polar coordinate system. But if I want to be able to rotate out and away from my palm, that's where that third angle comes in. So I'd have the distance, that would be my r. I'd have the first angle, that'd be the angle around my palm, and then I'd have the second angle, phi, which would be the angle either out towards or back away from the camera. Not the z, but again allowing to move me in the z direction. And what we're going to find out is that anything you can describe with an x, a y, or a z, or a combination of those three, you could also describe in a polar system using some combination of the polar coordinates.